Hello everyone and welcome back to this next lecture in the machines lecture series, and this is where we had left off in the previous lecture where we had stopped at creating some static variables for the machine parameters, and this was so that we can optimize our machine parameter calculations such that it occurs only once at the beginning of a simulation. And this is the reason because we felt that the machine parameters will not change that much with time, and even if a change needs to be simulated, we don't need to calculate the parameters all over again. We can introduce changes in the parameters in a different manner, which can be dependent on temperature or any other factor. So now that we are done with this, we can now start with the actual machine model. And in this lecture, I'm going to talk about what is the machine model, how are we going to go about it, and in general, what does it take to create any mathematical model for any physical system. So, as always, before I start the lecture, a little bit of brief background that if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length online courses that you can access on my own website, which is pythonpowerelectronics.com. So this website, which is pythonpowerelectronics.com, contains almost all the information related to this particular project, which is including all the courses, the books, and any other material which is needed. So to access the courses which are available, you need to click on the button which is called Learn. And this takes you to the page with the courses so far. So I have 5 courses so far, and I'll go through them. The very first course I have is Simulating Power Electronic Circuits Using Python. And in this I talk about the basics of how you can use Python and Python Power Electronics to simulate power electronic circuits. The second course I have is called Basics of Digital Signal Processing for Power Engineers. And in this I talk about how you can use Python and Python packages like SciPy and Signal to design and analyze filters for power engineering applications. The third course is Simulation of Magnetics for Power Electronics using Python, and in this I talk about how you can use Python and Python Power Electronics to model magnetic components such as inductors, coupled inductors, and transformers specifically for power electronic applications. The fourth course I have is called Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and Python packages like SciPy and Python Control to analyze and design controllers for power electronic applications using the example of a single phase grid connected converter. And the last course I have is Why Specialize in Power Electronics, and in this I talk about the challenges and opportunities available in power electronics. So this is a free course which is targeted towards either high school students or even junior undergraduates who are yet to choose their specialization, and this is to sort of motivate them to choose power electronics as their domain of specialization. So all these courses are available on 2 forums, which is Decibels Labs and Udemy, and clicking on the button will take you to the course page. The link for this page is provided in the description of this video, so if you're interested, please do check it out. So with this, I will go back to the lecture. So here we had introduced these static variables, and as I said, we already had changed the code to initialize this simulation, or rather perform these simulations or other calculations at the beginning of the simulation. And then we had reset this variable so that this calculation does not occur again, and we had verified that fact. So let us go back to the equivalent circuit to figure out how we're going to model this. So as I already said, the purpose behind this equivalent circuit of the induction motor was to generate all these parameters with which we can now write equations, right? And this is the basis of any mathematical simulation. That is, we need to come up with a mathematical model which comprises of equations that describes any physical process. So for this, I will need to actually go to the diagram of the motor. And let's try to figure out what we're trying to do here. So, if we want to simulate this motor, the question is, what do we need to do? Let's try to figure out this step by step. So first and foremost, what is the independent variable, or rather what is the independent effect on this motor? And this effect on the motor is typically the applied voltage, right? This voltage which is applied, which is a single phase voltage, which is applied to the stator of the machine, is the independent voltage. This voltage, though we choose as a sinusoid, can have certain fluctuations. It can have spikes, it can have sags, it can change, there can be changes, there can be flickers. And all these changes will have an impact on the motor. So therefore, our model must reflect the effect of this voltage, which is of course an AC quantity, and also it must reflect any changes in the voltage on the machine itself. The next independent variable is the load, and this load here is represented here as the wheel. So for example, this is the rotor which is mounted, and typically this is the shaft. This is the shaft of the rotor. So this shaft of the rotor is used to mount the rotor. So you can see here that these two end plates are connected to either side of the stator, and this enables us to mount this rotor inside the air gap of the stator, right? This is of course essential because otherwise this can't hang in the air, right? So now that we have this shaft here. To this shaft we can further couple a mechanical load, right? Now in reality, any motor performs some kind of a mechanical work. For example, it could be a pump, in which case it may be pumping some kind of a liquid. It could be oil, it could be sludge, it could be anything. For example, it could be an oil and gas platform where you're using pumps to pump out sludge as you dig, as you dredge. Or it could be an electric vehicle where the mechanical load is the actual car which is actually moving, right? Every time you accelerate, you want your car to move forward. So this moving forward is a mechanical work that is being done by the motor, right? So in that case, the transmission system of the car is connected to this shaft. Of course, it's going to be way more complicated. Electric vehicles usually are, but conceptually, this is what happens. Now, we need to also capture some dynamics of the mechanical system. So for example, if there is a particular load, and that load is usually represented as a load torque, right? It could be, we could represent it as just a simple moment of inertia. So for example, if we know the weight of a particular, let's say it's a car, if we know the weight of the car, if we know the speed of the car, then this translates into a load torque. And that load torque is the mechanical load torque, which is the external input to the motor. Now, in order to be able to simulate the mechanical system, we need to know what is the actual electrical torque that is produced, or rather the mechanical force. And this force minus the load torque will result in the acceleration and the speed of this motor. So this is the mechanical system. So here we use simple Newton's law. We use force is equal to mass into acceleration, right? Of course, since it is a rotational machine, we will use torque is equal to inertia into angular acceleration. Now, this is the independent variable. So we said the independent variable is the voltage and the load torque. Now let's try to figure out what else is happening. Now, we are applying a voltage. Now that we apply a voltage, as I said, this voltage will result in these are stator windings. So voltage is applied to the stator. Current will flow in the stator. This current which flows in the stator produces a magnetic field. Most of the magnetic field will be associated in this air gap, right? Some part of the magnetic field will leak into the air outside, right? If it leaks into the air outside, it doesn't do anything useful. It is leaked flux, which is useless. But the flux which remains in the air gap is the flux that associates with the rotor. Now, since we are applying an AC voltage, the flux produced is also changing. It's an AC flux. As per Faraday's law, whenever the flux associated with any conductor changes, this results in an induced EMF. So this means that the flux in the air gap is being associated with the stator and also with the rotor, right? Remember, any conductor that is in a changing magnetic field will experience an induced EMF. So therefore, an induced EMF will be present in the stator and also in the rotor. Now, the induced EMF in the rotor, because we have a squirrel cage induction motor which consists of bars which are short circuited, the induced EMF will result in currents flowing in the rotor. Again, once current flows in the rotor, in any conductor, it will produce a magnetic flux, right? So in the same way that the current was flowing in the stator winding, produced magnetic flux in the air gap, the current that is flowing in the rotor bar will produce a flux also in the air gap. Right? So now we have two magnetic fluxes. We have the stator flux, we have the rotor flux. Now, if you go back to the very basic principle of magnetism, if we take two magnets and bring them together, they will either attract or they will repel. Opposite poles attract, the similar poles repel. If we bring a south pole and a north pole together, they will attract. If we bring two south poles together or two north poles together, they will repel. Whether they repel or they attract, if we bring two magnets together, a magnetic force is produced. This magnetic force is the result of two magnetic fields interacting with each other. Right? And this is basic physics. When two magnetic fields interact, there will be a force produced. So therefore, with this stator flux and this rotor flux, since they are both present in this air gap, these two will now interact and produce a magnetic force. This magnetic force will result in a torque, and this torque will cause the motor to rotate. So this is what we need to simulate. We need to simulate the fact that when we apply a voltage, it results in a magnetic flux. This magnetic flux will result in an induced EMF, and this induced EMF will also produce a magnetic flux. And finally, these two fluxes will interact to produce a force, which will cause the machine to rotate, and the force minus the load torque will decide the acceleration of the rotor. So, on a high level, this is what we're going to do. Let's go back now to the details and try to figure this out. This voltage is being applied here. As I already said, not all of the voltage, or rather the current flowing, it's like this. The voltage which is being applied will result in current flowing in the stator windings. But not all the current in the stator winding will result in useful flux in the air gap. Some of it will leak. Right? And when we are talking about leakage, the leakage could be anywhere. It could be somewhere outside, right? So it doesn't go into the air gap, it goes outside, it could go somewhere else. It's not doing anything useful, that's all, right? So this leakage we have already represented by this leakage reactance or inductance of the stator. Besides that, we also have a stator resistance. So therefore, this stator resistance will result in a drop. So this stator resistance and this leakage inductance will result in a certain voltage drop such that this voltage drop does not do anything useful. Now here we have taken into account the core loss resistance and the inductance, mutual magnetizing inductance. This magnetizing inductance is the inductance that is responsible for producing the flux in the air gap. Right? So the current through this magnetizing inductance is responsible for the stator flux. Right? But remember, we have here a coupled system. So therefore, it's not just the flux in this air gap is the result of the stator flux and the rotor flux. So we have to take into consideration the fact that the stator flux is impacted not just by the current in the stator but also the current in the rotor, because this is a magnetically coupled system. Remember, whenever we have a magnetically coupled system, current is due to the self-inductance, or rather flux is due to the self-inductance as well as the mutual inductance. So this magnetizing inductance is the major part of the self-inductance of the stator. But we also have to take into account the current flowing in the rotor. That also impacts the stator flux. Now, once we do prepare the stator flux, we have to take into account the rotor flux. And here too, we will take into account the mutual inductance between them. So we do take into account that the current flowing in the rotor may be impacted by the current flowing in the stator. Of course, these will be details, right? So we can establish using basic electrical equation. That is, we can use Kirchhoff's voltage law to state that the applied voltage will be equal to the drop across the stator, the drop across the leakage inductance of the stator, and the induced EMF. So whatever that comes across this parallel branch is the induced EMF. Right? So now this induced EMF is, as we already said by Faraday's law, equal to the rate of change of stator flux linkages. And as I already said, stator flux linkages can be expressed with respect to the current in the stator and the current in the rotor, as well as the inductances. The same can be said about the rotor also. In the rotor, we can say, of course, in the rotor, because we have a squirrel cage induction motor, the voltage at the stator is zero because it's been short circuited, right? If we had instead a wound rotor induction motor, then in that case we would have a rotor winding with slip rings that could be taking it out. You could apply an external voltage, but in this case it's a squirrel cage induction motor where the rotor consists of bars that are short circuited. So there cannot be an applied voltage at the rotor. Therefore, there is no applied voltage. The applied voltage at the rotor is zero. All that matters is the current in the rotor versus, or rather the voltage at the applied, or rather you can say the applied voltage at the rotor is zero, and the induced EMF is equal to the rotor drop, right? The drop across the rotor resistance, and the induced EMF across the rotor. And once again, the induced EMF across the rotor will depend on the self-inductance of the rotor and the mutual inductance with respect to the stator. With this, we will result in two equations. So we have the induced EMF at the stator and the induced EMF of the rotor. The induced EMF of the stator will reproduce the stator flux linkages. The induced EMF of the rotor will produce the rotor flux linkages. Once we have the stator flux linkages and the rotor flux linkages, we can calculate the electrical torque that is produced because of the interaction of these two fluxes. And once we have that electrical torque, we can assume or we can calculate some form of electrical torque to find out what is the acceleration of this rotor and therefore what will be the speed, because this is after all a simulation. It's a time simulation. So this is the basic simulation of a motor. Of course, you can come up with more complex. Like I said, any phenomenon that you want to simulate, you must express mathematically. We have expressed the most basic physical phenomena, that is how a voltage applied results in an air gap flux, how that air gap flux results in induced currents, which in turn produces a flux, and these two fluxes interact to produce a torque. This is at the most basic level. If you want to simulate more complex phenomena, like you want to simulate the vibration in the rotor, you want to simulate various other effects, in that case you must express equations for that physical phenomena just the way we did here. And once you have that physical phenomena, you have to solve those equations in the simulation along with the basic simulation equations to produce your more complicated or rather enhanced simulation model. This is all there is to simulations. So the reason for this lecture was that quite often we just begin by writing equations, and sometimes if you are not totally well prepared with simulations or you have not been simulating for a long time, approaching the simulation of any physical system is sometimes a bit daunting. So for example, here we have a machine. This is a machine which takes an electrical input, produces a mechanical output. But for a novice, for somebody who is beginning, it is sometimes quite mystifying as to how we can express this entire system as a set of equations which we can solve. But this is all there is. It's important that whatever you simulate, whenever you simulate any system, you must take into account the inputs, and you must be able to link starting from inputs through all the physical phenomena that are affected by these inputs. the way we did here. So more details will come when we actually start simulating. So now that we have this basic picture, in the next lecture, I will start writing equations using this equivalent circuit, using the parameters, because we have calculated these parameters. All we have to do is now start using them, right? We can just start using these parameters to create our mathematical model. So if you have any doubts, please do either send me an email or message me on social media. Otherwise, I will see you next week, where we will actually start writing some code to simulate the motor. Thank you so much for watching, and see you soon. Goodbye for now.